Hello everyone, welcome to another robotics session. Today we're gonna continue our inverse kinematic discussion. We said that we can get the inverse kinematics by optimizing the forward kinematics, and different methods we proposed that would give us essentially something we call a pseudo-inverse. And using this we can calculate joint inputs for a desired end effector position and velocity. But one question is that what happens if there is singularity? How can we avoid singular positions of the robot when the rank of Jacobian drops? Today we're going to discuss some methods that we can use to avoid singularity. But one option that you can think of is using robots' secondary tasks. Previously we said that the robot that is redundant has an option to do secondary tasks. Consider the case the robot that has 4 joints wants to do a task in 2D. This robot will have some singularity positions. For instance, when all of the robot's links are aligned with each other, this is where the robot suddenly loses degrees of freedom in this direction. And Jacobian at this point will become rank deficient, uninvertible. You might think that using pseudo-inverse we can probably handle it, but the fact is when Jacobian drops rank, regardless, pseudo-inverse will also drop rank. By looking at the equation for the pseudo-inverse, when Jacobian drop ranks, its inverse would go toward infinity, or some of the columns it becomes 0. Still, in the equation for pseudo-inverse, this part will go toward infinity, and Jacobian pseudo-inverse Jacobian is still not obtainable. So we need to think of different ways. One way is to consider secondary tasks. We said the redundant robot like this can move its joints without affecting the position of end effector. Consider we want to get to the point here when there is a singularity in our configuration. How can we avoid it? We can build a secondary task that makes sure we never reach these joints. If we want to get here, let's get there using this configuration. Our secondary task would be to make the distance between the joints to their singular configuration as far as possible. This is a nice idea to use secondary tasks of a redundant robot to avoid singular positions. To do that, we need to first formulate secondary tasks in redundant robots. How can we show and separate a secondary task from a primary task? Again, we go back to optimization. Consider we propose to solve the inverse kinematic problem using optimization with the new cost function here. Previously, we used kinetic energy as a cost function, but this is a bit different. This cost function is equal to this. The distance between the robot's joints and a joint that we defined, we call it Q0, a joint configuration, a specific joint configuration. If we minimize this cost function, we're making sure that our joints are as close as possible to Q0, the joints that we have in mind. This is a way that we bring in the secondary task. Assume our secondary tasks are performed using Q0. This will make more sense later throughout the video. But let's select this cost function and try to minimize it. We follow the Lagrange procedure. We consider this is our cost function that we define now, and this is our forward kinematics that we use as a constraint. We need this to be always satisfied. We use Lagrangian to minimize this cost function, taking derivative of our new Lagrange equation with respect to q dot and lambda, the Lagrange variable, we get these two equations. From these two, we can calculate lambda as this. Putting lambda back into this equation, we can calculate q dot. If we simplify this equation, we reach to this equation. If we look at it, this is our pseudo-inverse, and this is also our pseudo-inverse. Replacing these two terms with pseudo-inverse, we get the final result. This is an inverse kinematics equation using our new developed cost function, and it has very interesting features. First of all, you can see that the first part of this inverse kinematic equation is similar to what we had before, pseudo inverse times x dot, and it has this part. This part is new, multiplied q dot 0 secondary task joint variables. What does equation mean? The fact is that this second part is what we call a knowledge-based projection. Remember from previous sessions, we said Jacobian looks like a mapping. For a redundant robot, it always maps a certain part of the configuration space into 0. If the whole mapping is J, the mapping that maps the joints into 0 is given by this equation that we just derived. I minus pseudo inverse of Jacobian times pseudo inverse of Jacobian. Look at this equation. The second part is the mapping that maps joint inputs to 0. To understand it better, we can look at the equations a bit more closely. Consider this is our new inverse kinematic that we just derived for secondary task cases. Let's put this back into the forward kinematics. Forward kinematics equation was q dot, right? Now let's replace q dot into this equation, see what happens. So if you remember from previous session, I showed some features of the pseudo-inverse, and one was that this term is actually equals to j. So these two will cancel out and be 0. So essentially x dot is j pseudo-inverse of j x dot. Let's replace the equation from pseudo-inverse in here. So you can see using this new pseudo-inverse that we developed, the new inverse kinematic that we developed, we replace it in the forward kinematics, and the result cancelled out and showed x dot is equal x dot. Basically, this part, this second part, had no effect on the end effector velocities. This is what we call the knowledge-based mapping. So any joint motion q0 dot multiplied by this knowledge-based mapping will have no effect on x dot in the end. And this is where the secondary tasks come in play. We can use this q dot 0 to do secondary tasks, because no matter how this changes, no matter how q dot 0 changes, it will not affect the final end effector position. These are the self motions of the robot. These are the motions of the joints that doesn't change the position of the robot. And we can use this to do secondary tasks. One of them could be avoiding singularities, for instance. I'm going to give you a couple of examples of secondary tasks. One, let's say we want to use q dot 0 to avoid singularity. How can we do that? We can build a cost function that ensures we never reach singular positions. If you remember, singularity Singularity happens when determinant of the Jacobian was 0. How about we try to play with Q0 to make the determinant not 0, maximize it. That's a good idea to avoid singularity. We can build this cost function here I call W, which is a square root of determinant of J times J transpose. This is essentially like determinant of J squared. So when this W is maximized, it goes far away from 0, then we don't have singularity. Now let's use Q dot 0 to maximize this W. How can we do it? Using this equation. If Q dot is equal to gradient of this cost function, then it's always going upward far away from 0. If this is my W, I will go up and go far from 0 if I move in the direction of its gradient. So if I select Q dot 0 as gradient of this cost function with respect to Q multiplied by a positive constant, then it's always trying to maximize determinant of Jacobian, avoid singularities. Sidebar, how do you calculate this term? In practice, you should do it numerically. W is a number. Is determinant of J multiplied by J transpose squared. It's a number. Derivative of it with respect to Q, how is it calculated? Remember, it's a gradient. It would be derivative of W with respect to Q1, W to Q2, W to Qn. This would be our term. So we set Q dot 0 equal to a constant multiplied by this term. And sometimes in practice you want to calculate these analytically. So derivative of W with Q1 at each time instant you calculate it. You calculate W at, let's say, one time instant, then subtract it from the W that you calculated at previous time instant, divided by the change in Q. This would be gradient of W with respect to Q. Put them in a vector, then set them as the Q dot 0 when you're using inverse kinematics. This will move the robot to the desired position while playing with the self motion of the robot that has no effect on robot end effector to avoid singular positions. There would be other examples as well. Let's think of this redundant robot again. Assume it wants to go and pick an object, let's say here. And there is a wall here. We want the robot to go toward the object without hitting this wall. We can use secondary task. We can say that our secondary task would be avoid hitting the wall while you're doing that task. How can you formulate it? All we need to do is build a cost function that ensures our secondary task is satisfied. Let's say position of this wall is given by xd, yd, right? And the position of this end effector is x, e, y, e. All we need to do is build a cost function that makes sure the position of end effector minus the position of the wall is always maximized. It's bigger than 0, because if it's 0, we're hitting the wall. Then you can select your secondary task as derivative of this cost function with respect to Q. So we're changing Q zeros in order to maximize this, always move in the direction of its gradient. Then when you use this in your inverse kinematics with the secondary task capability, it will always ensure to avoid the wall. And keep in mind that the secondary task depends on the size of the knowledge space of the robot. We talked about the nullity dimensions. A robot that has more degrees of freedom in its nullity space is more capable of doing secondary tasks. For instance, this robot has 4 joints and wants to do a 2D task. And let's just say it wants to move its position of end effector. We're not interested in its angle. Then it has a degree of nullity 2. The range of Jacobian is 4. The rank of the Jacobian is 2. Nullity is 2. It can play with 2 joints to do secondary tasks. If we wanted to do it better, we use a robot that has nullity of 3 or 4. So increasing redundancy gives us more capabilities to do secondary tasks. There are other ways to avoid singularity as well. One was secondary task. What else we can do? Another thing we can do is to use something that's called damped Jacobian. A damped Jacobian is like a pseudo-inverse, but the difference is this term added. If you remember the pseudo-inverse equation and compare, this has a small term added. What does this term do and where does it come from? It comes from another optimization method used to get the inverse kinematics. If we use this cost function as our cost function when we want to find the inverse kinematics, we drive this damped J, or sometimes call it damped least square inverse. What is the difference? In here, our cost function is to minimize the square of the joint velocities while minimizing the forward kinematics equation. What does it mean? When you minimize the forward kinematics equation, you're actually ensuring that the changes in the Jacobian are small. In other words, you're making sure that its inverse won't go to infinity. This is a way to avoid singularity. If you look at the damped Jacobian inverse here, the term added K2 identity is like a term that adds some elements, very small elements, to JJT matrix in the diagonal elements of JJT. What does it do? It increases the size of the eigenvalues of JJT matrix. Therefore, it makes the inverse of J or its determinant larger. Make sure it doesn't go towards 0. These are some concepts from linear algebra. This was a FYI. It's important to know this matrix. This also exists and it can avoid singularity. How it is derived doesn't matter that much. Finally, there is a third way to avoid singularity. What is it? This is a very simple method. Instead of solving the inverse kinematic, assume that the Jacobian inverse is given by Jacobian transpose. So previously we said Q dot could be pseudo inverse of Jacobian times X dot. Now assume that it is transpose of Jacobian. Why does this method work? We will see in the next few videos when we talk about dynamics. But for now, let's assume that this method also makes the robot avoid singularities. To recap, in these 2 videos so far on inverse kinematics, we talked about how to get the pseudo-inverse for a robot that is redundant. We got several equations for pseudo-inverse using least square methods or using Lagrangian. They can all be used to solve the inverse kinematic problems. Second, we introduced concept of secondary tasks. How can we use inverse kinematics while doing a secondary task? We showed that there is a Q0 element that we can play with without affecting the robot end effector position, and that Q0 can be used to optimize something we want and do the secondary task. And we said we have several options to avoid singularities. One is to try stay away from singularities, considering it as a secondary task. Another is use a damped least square. The equations we had was similar to pseudo-inverse, but it has a small term added to make sure the Jacobian is invertible. And finally, the simplest one is to use Jacobian Transpose instead of Jacobian Inverse. In terms of performance, this is the best one, and then comes these two. And so keep in mind that avoiding it as a secondary task is the best option, if not possible, if your robot is not redundant, doesn't offer secondary task capability, we can use least square damp and then finally Jacobian transpose. That is it for today's session. In the next videos, we're gonna stay away from kinematics and move a bit toward dynamics of the robots.